Okay, well, you got me here with a video for one more day as I'm recovering from my knee replacement. And with your set of things that you did coming into class, we dealt with the integrated rate law, collision theory, and the Arrhenius equation. We're going to practice those things with our class time today. We're going to work problems with me, hopefully finding out that you can make sense of your notes as you bring them into class. Now, for your reinforcement of that, you will be doing sapling numbers 15 and 16, which will be due our next Monday at 6 p.m. We're going to finish up this chapter, chapter 14, which is our kinetics chapter, with a couple of topics that you see there. And then we're going to go and delve into a whole new chapter with your next set of videos dealing with chemical equilibria. Now, when we start this section on chemical equilibria, it is a beginning of a very long multi-chapter topic. So you've got to make sure you keep pushing to understand each day, because we're going to be building upon that understanding. And if you don't build up a good scaffolding, you are going to topple it over. So be asking questions, be making sure you're understanding as you go. Utilize your textbook and the example problems that are there as well. Okay, so let's go ahead and jump into getting out your notes and seeing if you can make sense of these things by using your notes. So at any point when you see this, you pause, you start digging and see if you can obtain the answer. You're pausing, I'm continuing on, and I'll work the problem so that when you come back you can see, did I do it right? And if you did, great, move on. If you didn't, back up and watch my explanation. Okay, so we're trying to determine the half-life. What do we know about this? It is a first-order reaction. That is a key statement there. It is a first-order reaction. We have a half-life equation that applies only to first-order reactions, and that is, it is 0.693, which happens to be the natural log of 2, over K. So in this problem, we were told the half-life, and we're trying to obtain the value of K. So let's put the information in. Actually, let me go ahead and just solve for K. Therefore, K is equal to 0.693 divided by the half-life. So I take 0.693, it has no units, and I divide it by the 35.0 seconds, and that is going to give me the constant, the rate constant for this experiment, and I got 0.198. And what are the units? No units on top, a seconds on the bottom, so 1 over seconds. That is our unit. Whenever we have a first order reaction, it's always the unit of K is 1 over seconds. All right, let's go to the next one. Oh, I've already told you that, okay. That's what I wanted you to tell me first. That's a good check, okay. But you ought to keep that association going in your mind. First order of the K is 1 over seconds. And there's the value that we have determined for this one. Doesn't work as well when we're not in class and me pulling up these with you all answering. All right, here we have a first order reaction. The half-life is given to me there, so it's the exact same problem we were working on before. And now I want to give you some information. We know it's first order. We know the K. We know the half-life. Okay, I have that. That's all here. Now we're going to start with a 32-gram sample, and I want to know how much time is going to remain, how much of that 32 grams will remain after 70 seconds. Pause, think about it, and select your answer. Well, did you pick 8, and were you able to do that fairly quickly, or did it take a lot of calculations? Whenever I'm given a time like that, 70 seconds, I look back at my half-life and see if that's a multiple of that. It is 2 half-lives. 2 half-lives. Right? It's going to get cut in half twice. How much did I start with? I started with 32 grams. I cut it in half once, and I'm down to 16 grams. I cut it in half again, and I'm down to 8 grams. So that's the first half-life, that's the second half-life, and we are set with that. Now, you may or may not have done it that way. You can use the natural log equation, and we'll do another problem with it where we're using the natural log equation, and you can actually plug numbers in. But I love looking for that little trick. Is the time that they give me a multiple of the half-life of the problem? And if so, I can just cut it in half that many times. 70 seconds is 2 half-lives. All right, let's go to another problem where you can't do that. To do our next problem, we have to think of this question before we do it. If I gave you a problem and I said that 95% of phosgene, that's the pH3 you see up there, if I said that 95% of the phosgene had decomposed, what amount of it would remain? Well, did you pick C? 5% would remain? Right. If you start with 100%, 95 goes away, you're left with 5% behind. So we're going to work a problem using that piece of information here, okay? It's the same reaction. I want to know how much time goes by to allow for 95% of the phosgene to decompose. If it was 50% of the phosgene to decompose, hey, it's 35 seconds. This is not 50%, okay? 95% of it's decomposing, so 5% of it remains. Here, I would like for you to stop and try it on your own, or kind of let me get you started. At some point, stop and try to finish it, and come back and see if you got it right. The equation we're going to use is the first order integrated rate law. The natural log of A over A naught is equal to a negative KT. We're trying to figure out the time for 95% of it to decompose. So that would be the natural log of, well, I started with 100%, so I'm going to put 100 down there. And I finished with 5% remaining. So you got to be really careful in how the wording of the problem is. It could have said, what is the time required for 95% of the phosgene to remain? If 95% remains, okay? It didn't say that. It said 95% of it reacts. What goes in here is how much is still in the reaction chamber, so it's 5%. And that is going to be equal to a negative, and there is my K value, 0.198 1/seconds, and I can solve for the time. Okay, so let's see. I've got some numbers here that I would want to work with. Oh, well, I didn't. I didn't break it apart when I did it. So let me break it apart with you guys right now. You take the natural log of 5%. So that's the natural log of 0.05, right? Let me take that. And that was a negative 2.996. I'm carrying extra sig figs. I could probably do a negative 3 there. I'm going to double check that. Yes. And that is equal to a negative 0.198 1/seconds. This has no units, times time. Okay? So then I can divide both sides by the negative 0.198 1/seconds. And that will give me my time, right? That will give me the time. And the time ends up being 151 seconds. Okay? Now, how do I know it's seconds? Well, it is 1/1/seconds. We're dividing by a fraction, which is the same as multiplying by the reciprocal. That gets the seconds up there on top. So that is how you do an integrated rate law. Now, this is, in the wording of the problem, a first order reaction. So that's how I know to pull out this equation. Okay? If it were second order, we would have a completely different half-life equation. We would have a different integrated rate law. So it's very important that you're reading through and finding out whether it's first order or second order when you're doing these problems, so you pull out the right equation. But otherwise, it's just a matter of plugging in what you know and solving for what you don't know. And before I leave this problem, let's go back to the how much remains after, what was it? How much remains after 70 seconds, okay? They gave you how much you started with, and this was this problem here. They gave you that I had 32 grams. You can use grams, you can use molarity, you can use number of particles. Because it's the same in the numerator and the denominator, the units are going to cancel out, so it doesn't matter. We're solving for this in this problem. We know our K and we know our time. 70 seconds, our K is 0.193. So if you don't see that this is 2 half-lives and just cut it in half twice, you can solve algebraically for that number and you can get an 8 out. You might want to do that as a practice, okay? You might want to solve for A and say, did I get 8 grams for that number? All right, so that's our practice with the integrated rate laws.